Dear friends, welcome back to one more lecture session on introduction to system design. Today we will discuss about the operational architecture development of engineering systems. Operational architecture also is known as allocated architecture. So, we will be discussing about this particular allocation of architectures for the system in this class. In the previous lectures we discussed about the physical architecture development as well as the functional decomposition, and then we saw that how the functions can be allocated to physical system and the physical architecture can be developed, where we can have a hierarchical architecture which can be used for identifying the systems and subsystems and assemblies and so on. But that alone is not sufficient. We need to look at the operational architecture, especially when it comes to the internal architecture of the system. There are many things which actually could not be identified in the direct physical architecture development. So, we will look at these aspects of the system development today. As you can see, we were discussing about the 6 functions of the design process, and then we completed the first 3, that is the system level design problem, functional architecture and the physical architecture. The next one is system operational architecture. So, we will go to the details of this one. So, operational architecture is basically the development process for the operational architecture, or also known as allocated architecture, which is the activity during which the entire design comes together. So, this is the stage where we try to put everything together: physical systems, the operational details, and the internal requirements, the technology and system wide requirements, all those things are put together in this stage, and that is the operational architecture development. So, it actually integrates the requirements decomposition with the functional and physical architectures. So, we have the requirements decomposition and we have functional and physical architecture. So, we try to integrate these things together in this stage, and it provides a complete description of the system design and provides the raw material for the interface definition as well as trade-off decisions. So, as you know, in the physical architecture development we have many systems and subsystems, and we need to have this system and subsystem interface also along with the model. So, we try to have the interface definition as well as the trade-off decisions and the corresponding architecture also in the operational architecture development. In trade-off decisions are basically whether we need to increase the cost or we reduce the cost in lieu of performance, or we try to have some other reliability or some other aspects traded off for some other performance aspects. So, all these decisions also need to be taken, and that also to be analyzed and implemented in the system architecture. So, in the operational architecture or the allocated architecture, we try to incorporate these features and then complete the system architecture, or try to integrate the physical requirements, the functional architecture and physical architecture to get the system's operational architecture. So, that is the scope of this particular section. So, the major activities involved in allocated architecture development are listed here. The first one is allocate functions and system wide requirements to physical subsystems. So, we discussed briefly about this in allocation of functions in the functional architecture. So, in this stage we will actually allocate functions and system wide requirements to physical subsystems. So, there are system wide requirements like technology, cost, reliability, manufacturability or efficiency. So, these are the system wide requirements. So, we need to allocate these requirements also to components. So, which component will actually provide the required cost effectiveness, or which component will increase the reliability of the system. So, that way we need to allocate the components to system wide requirements also. So, that is the first stage where we try to allocate functions to components based on already identified requirements as well as the system wide requirements. And then based on this we allocate the functions to components. So, functions, initially we identify the functions and the requirements and the functions, and then we try to allocate them to the components. So, there are different methods of allocating the functions to components, we will go through it later. Then the trace system wide requirements to system and derive component wide requirements. So, we have the system wide requirements. So, we need to see how these system wide requirements are implemented in the architecture. So, we have to trace these system wide requirements to the system and its components. So, not only to the system, we can actually easily identify the system wide requirement to the system and we can say is provided, but we need to identify which component is actually providing this requirement, and that is the tracing of system wide requirements to system and derived component wide traces. The next one is define and analyze functional activation and control structure. This is basically to find out when a particular function should be activated, or what are the input commands coming to activate the particular function. There are many sub functions or bottom level functions. So, each function need to be activated at a particular stage. So, that is the activation signal coming to the function, and we need to identify which is that signal which activates the particular function, and what are the other control structures needed, what is the precedence of a particular function, whether this function need to be activated at before the previous function or it has to succeed a particular function. So, that is the control structure. So, we will try to identify the activation functions or the signals as well as the control structure of the function in this stage. So, that also is included as part of the architecture development, and then conduct performance and risk analysis. So, what are the risks involved, or which are the elements of higher risk, or how do you distribute this risk, or how do you identify the element which actually is of high risk in particular operation. So, all those need to be identified at structure development level itself. So, therefore, we do an analysis to performance analysis to identify the risk involved in the subsystems as well as components. And finally, we document the architecture and obtain approval. So, these are the major activities involved in allocated architecture development. So, as I mentioned, we start with the allocation of functions to elements, especially we look at the system wide requirements and then try to identify the functions and then allocate them to components, and then we trace these requirements to component wide system or component wide. So, we try to ensure that there is a traceability for these requirements, and then functional activation and control structure will be identified, and then a risk analysis will be carried out, and finally, we document the architectures and obtain approval. So, that is the different steps or different stages involved in developing the allocated architecture or the operational architecture of the system. So, we will go through one by one and then see how actually we can do carry out these activities. To represent these activities, the major activities of this development are shown in the IDEF0 diagram. I hope you are now familiar with the IDEF0 diagram because we use it for the functional decomposition. So, if we represent the process using IDEF0 diagram, you can see that these are the major functions. So, you can see here these are the functions 1141, 1142, 1143 and 1145, okay, so this is 1144 and 1145. So, these are the 5 functions identified in the architecture development, and then you can see what are the inputs and outputs. So, here the for the first one, that is allocate functions and system wide requirements to physical subsystems. The inputs are originating and system requirements, objectives, hierarchy, and qualification boundary and qualification requirements is one of the inputs, and then system level functional architecture, which we already developed, is another input. Then the physical architecture, the candidate physical architecture, which we identified in the physical architecture development, is another input, and then the other inputs are the system level operational concept, which is coming from the initial stages, and that will be going as an input. And using all these inputs, there will be an output coming as functions to subsystem allocation. So, this is the output from this. So, you have the functions which are allocated to subsystems, and then define and analyze functional activation and control structure. So, this as I mentioned, we need to find out how these functions need to be activated, or what should be the signals which actually activate these functions. That is to be identified here. So, here actually the output will be an alternate system level operational architecture. So, we can actually get multiple operational architecture, alternative architectures, because we can actually put it in different order, different format. So, you will be having multiple architectures. So, that will be the output from this stage, and then you can actually choose one of these architectures and then do a performance and risk analysis, which is the output will be the analysis results, and then that will be going to the documentation for approval, and that will be going as also document subsystem specification. So, you can actually develop the subsystem specifications based on this analysis. So, output from these different stages will be coming, and one will be approved for sent for approval, and the other one will be used for subsystem specification development. So, you can see these are the various outputs coming over here. So, this is the operation architecture document, this is the architecture changes, whatever the changes taking place, and this is the operation architecture finally you are getting, or the allocated architecture, and then the subsystem design requirements, boundaries and objectives and constraints, all these will be developed or specified using this one. This is how we actually represent the various stages using an IDEF0 diagram. Let us go to the details of allocation of engineering functions to components. This is what I mentioned, we have to allocate the functions to components, because we have the functions identified in the functional architecture and we have the components identified in the physical architecture. So, we will try to map these functions to components. So, what we try to do is to allocate the functions to components, we do not do the components to function because of various reasons. So, if we can actually have a mathematical relation type of allocation, basically we have some relationship between these components and functions, and I allot the functions to components. But then the problem here will be, because it is only a mathematical relationship, some of the functions will be left out and some of the components also will be left out. So, in order to avoid that, we need to go for a mathematical function type of allocation. So, we actually develop the mathematical functional relationship between the components and the functions and try to ensure that all these functions are related to components. That is different from this, where we do a mathematical relationship, there is a possibility that some of the functions will be left out. So, in this case the mathematical function method of allocation, we ensure that this complete mapping is carried out over here. So, here you can see that some of the components are mapped to more than one function and some of the components are without any functions also. So, this actually is a problem, because we have some components left out without any function, that it looks like the functional architecture was wrong, or we identified wrongly the component to provide functions. So, this can actually be approached in a different way. We can actually have a on-to allotment, that is, you can actually have all the functions and all the components used in the system, and we can allot these components also to some of the functions. Then another problem here will be, if you try to allocation, then that some of the components will be having multiple functions, or some functions will be having done by multiple components. So, like this, okay, in this case it is not shown, but there is a possibility that same function can be done by, okay, in this case there is a same function can be done by one component, and in some cases one function shared between two components. Suppose if the F2 is mapped to C2 and C3, that means these two components can actually do the function F2. So, this is also a problem, because we do not know how to aggregate this function between these two components. So, that may actually create a problem at a later stage. So, the best way is to do a one-to-one and on-to function for allocation. So, we will develop a function which actually maps all the functions to components on a one-to-one and on-to basis, that is one-to-one and then only one component to one function. So, in this way we can ensure that all the functions are mapped to components and all the components have definite functions identified using this one. As in the previous case, if you have separate same component having different functions, or one function being shared by two components, the uncertainty will be there about the level of distribution of function or the components. Or if you have two components doing the same function, that actually shows that these two components, one of the component is redundant. So, in the normal allocation you do not have to have redundant components unless it is for the error analysis or error reporting kind of fault tolerance system. Otherwise, we do not need to have two components doing the same function. So, all these can be avoided by going for a one-to-one and on-to function allocation, which is normally employed for getting or mapping the functions to components. So, that is the way how the functions are allotted to components. Okay, this is actually another view of the same thing for better clarity. So, you can see here, this is the mathematical relation type allocation, and this is the mathematical functions for allocation, and the last one is one-to-one and on-to function for the allocation of functions to components. So, this is the most preferred method, where we allocate the functions on a one-to-one basis as well as on-to functions. So, some of the important points about mapping the functions is, basically mapping of functions to components is chosen rather than mapping of components to functions. So, functions to components, not component to function. So, this is what I explained. So, we always do the functions to components because we do not want many components doing the same function, that will lead to redundancy. So, we will try to ensure that there is always a functions to components mapping rather than components to functions mapping. So, the requirement is to provide the functions, not to have the components in the system. So, we look at the functions and then map to components, and if there are any redundant components we will try to remove them, or we will try to identify separate function for the component, or if one component is doing multiple functions we will try to aggregate these functions into a single sub function and then provide refine the architecture in the functional architecture in such a way that these functions can be aggregated to a sub function, so that we do not need to go to further decomposition of that particular function because there is already a component which provides the function. So, this way we can refine the functional architecture once we complete the mapping. So, allowing two components to be mapped to same function must be avoided. So, this is I already explained. So, you cannot have two components to be mapped to same function. So, this must be avoided because if you do this, this actually becomes a redundancy. One way it becomes a redundant system, or the other it actually becomes difficult to aggregate these functions to components. So, which component will be doing the function, or whether they are sharing the function in a particular way, those things need to be identified or to be clearly stated. So, in order to avoid that we will try not to allow two components to be mapped to the same function. So, these are the two important points to be noted when we do the allocation of functions. And as I mentioned, when we do the allocation, basically there is a possibility that we can get alternative architectures, because when we have many ways of mapping the functions to one to one or one to functions, then the possibilities are that we can have multiple architectures, multiple allocation architecture can be developed, and then when we develop this multiple architecture we need to ensure that the choosing between these multiple architectures are done based on some objectives. So, if you have a particular design objective, then the selection of this alternative architecture should be done based on the design objective. So, we will try to optimize the objective. Suppose there is an objective that the system performance should be improved in terms of time of service, then the architecture which actually helps us to improve that particular objective to be chosen. Or in some cases, if we have a architecture or we have an objective to reduce the cost of operation. So, if that is an objective, then we need to select an architecture which will try to reduce the cost of operation rather than other performance parameters. So, like that, if depending on the objective of the system development, the architecture need to be chosen from the alternative architectures available. Similarly, we need to try to minimize the number and complexity of interfaces also. So, whenever we have options for having different architectures, we should look at the number and complexity of interfaces. So, whenever we have systems and subsystems, always there will be interfaces, and we need to ensure that these interfaces are minimum, so, or the complexity of interface is also less. So, if you try to choose a complex interface, then at a later stage when we develop the interface we find it difficult to provide the required functional specifications or functional performance, because the architecture is very complex. So, whenever we have a possibility or we have an option to choose an architecture, we should always try to minimize the number and complexity of interfaces. So, that is another point to be taken care of while choosing an architecture. Similarly, maximize early critical testing opportunities. So, whenever we have opportunities for early testing, that should be accepted. So, instead of going for many complex systems, if we can have small systems tested, or the testing procedure can be developed for small systems where a particular group of functions are performed. So, that kind of architecture should be chosen rather than the possibility of having a testing only towards the end of the development. That will be a problem, because you will not be able to do the testing in before the actual implementation or before getting the complete subsystem. So, we should always try to maximize the early critical testing opportunities for the systems and subsystems. And another important point is that equalize risks across the physical architecture. Okay, this is one of the requirements, equalize risks across the physical architecture. So, if you identify some risks in the system, try to equalize or distribute it evenly across the physical architecture, instead of making one system very highly risky, one particular subsystem risky, or some particular component very risky. Try to equalize them, the risk across the physical architecture. or localize risks in a single element of the physical architecture. So you can either distribute it equally, or you can have a localized risk in a single element. So we can actually identify the risks in those single elements and then see whether that can be all the risks can be localized to that particular element, so that we can ensure that failure can be at that point only. These are the different points to be noted or to be taken care of while allocating the architecture or selecting the allocated architecture. So since we can have multiple architectures, or we can have multiple allocated architectures, we need to choose one of the architectures, and when choosing this architecture, the focus should be based on these 5 points. That is, you try to optimize the design objective, you try to have simple interfaces or less number of interfaces, try to reduce the risk by equally allocating the risk to different components, or you actually localize the risk in one component and then choose that architecture for a particular system. Again, it depends on the final objective of the design and as well as the application and all other factors. So the selection of the architecture is purely based on the design team's intuition as well as their knowledge about the system and its operation. But these are the points to be noted and to be taken care of whilst choosing a particular architecture for the system. And there are different approaches for solving this allocation problem, because we have different ways of allocating the functions, especially when it comes to allocating work between the human and the computer or human and the machine. We need to ensure that there are some standards followed in allocating of these functions. So sometimes we can actually think of a completely autonomous system, or we can think of a system where the minimal autonomy is there and most of the works are done by the human. Because most of the systems are human centered and human operated systems, we need to ensure, or we need to find out what is the best possible way to allocate these functions between human beings and the machines or computers. So there are some standard procedures and standard principles developed by various researchers. So some of these principles can be employed in order to ensure that we have some standards in following the architecture or allocating the functions to the components. The reason why we need this is to ensure that we understand the importance of machines as well as components, computers, as well as the human in the system, and depending on the objectives of the design, we can allocate these functions to machines or computers, rather than depending on the ability of a system, the computer or a machine. We look at the system objectives and then allocate the functions. The computer may be capable of doing many things, but whether you really need it for the system or not is to be decided by the design team. So that actually comes from the understanding of the system performance objectives as well as the development objectives. Based on that, the designers can actually decide how to allocate these functions to machines or computers. So some of the principles used for this one is basically known as distribution of responsibility between human and computer. So that is the first. This was actually proposed by Sheridan and Verplanck in 1978. Of course, things have changed a lot during the last 40 years or so, but we can see that this actually gives a very general idea of what are the different ways in which we can allocate the function, that is depending fully on the human being for most of the tasks to the level where complete autonomy is given to the computers to carry out the task. So if you look at the top level, you can see human does all planning, scheduling, optimization and other tasks, and computer merely does deterministic execution. So it will actually do some calculation inside the system. It will not do any other work, because most of the planning, scheduling, optimization and all other things are done by the human beings only, and computer is just more used as a calculation equipment where it will do some deterministic execution of some of the tasks and just give the results without really making any decisions or any planning. All those planning, the scheduling and all done by the human operator. So that is one way of allocating the functions. The other one is the computer provides options, but the human chooses between them and plans the operation. The other one can be, we can find out the options, what are the possible options using a computer. If you want to arrive at a particular stage, or you want to move at a particular speed or particular location, you want to reach a particular location at a particular time, then we can actually ask the computer to do some calculations and find out the different options. So, if you take a different path, or you take a different speed, or you take a different altitude. So, these are the different options the computer can provide you, and based on these options the operator can take a decision, okay, which one to be chosen. Here the computer will take part only in giving you the options, not actually choosing an option. So, that is another level of implementation, or another level of using computer for the functions. The next one is computer helps to determine options and suggest one for use which human may or may not accept. So, this is slightly higher level, where it not only determine the options, but it actually suggests an option also. It will tell, okay, this is one of the best options at this stage, and whether to use it or not is actually completely left to the operator. So, here again the autonomy of computer slightly increases from the previous one. It is asked to give options as well as choose the best one out of the options given, and then the operator can actually decide whether to use it or not. The next one is computer selects action and carries it out if human approves. So, here the actions are selected by the computer and it carries out the operation if the human operator approves it. So, it is more autonomy. The computer has the autonomy to identify the possible actions and suggest the options and choose the option, and it will execute it only if the computer the operator says yes. That is, if the operator accepts the options and the action to be taken, then the computer itself will do the carry out the action. So, here it is much more autonomy for the computer. It actually identifies the task to be done and the options, and chooses the option and carries out the task. The next one is computer does entire task and informs human only if requested. So, this again top level autonomy. So, the computer does most of the work. It actually identifies all the options, it will identify the work to be done, and it carries out the work, and it informs only if asked by the human operator. So, if the human operator is not interested to know what is happening or what decision is taken, so it will not even tell the operator, it keep going on with its actions. And probably the highest level is the computer performs entire task autonomously, ignoring human supervisor who must completely trust the computer in all aspects of decision making. That is the fully autonomous system. You can actually look at some of the latest system. If you look at an autonomous robot, or if you look at the fly-by-wire system in the aeroplanes, so these are all actually examples of how we actually allocate the functions to human and operator. So, in the fly-by-wire system, most of the work can be actually carried out by the computer. Computer can find out all the parameters needed. It can identify the required thrust, required direction changes, required altitude. All those things can be calculated, and it can actually control this and maintain that one. So, unless the operator or the pilot wants to know this information will be available to the operator. Otherwise, it will be actually monitored continuously and maintained by the computer system itself. But in the case of an autonomous robot, if you take a completely autonomous robot, the operator actually plans everything and gives the task to the computer. The computer is doing all the tasks. It will get all the information from different sources. It will try to find out the tasks involved to meet the objectives, and finally provide the outputs, execute the task based on the information it provided with. And there is no way the operator can interface or interact with the robot at this stage, and it will be completely left to the robot to execute the task. So, that is the last. Operator has to depend on the computer in all aspects of decision making. So, these are the various levels of application or allocation of functions to computer. So, this was actually proposed by Sheridan long ago, and you can see that these various levels of this kind of allocations are implemented in various systems. So, depending on the requirement of the system, it is possible for the designer to actually choose any one of these and implement that as a objective, and then allocate the functions accordingly. Again, final allocation depends on the designer, because he knows what should be the level of interaction, level of allocation of functions to the computer, and accordingly he can allocate the functions. So, that is one way of doing it. And another method or another principle is basically for distribution of functions between human and machines. So, here it is not the computer, but basically there are different kinds of machines, automatic machines, semi-automatic, fully controlled by computer systems. So, how do we allocate the functions between human and machines in this case? And this was proposed by Price in 1985. And these are basically general principles. Again, it will not tell you how to do it actually, but basically tells that what are the binding principles on which the allocation should be based. First one says that there is no formula for allocation, imagination is crucial to allocation. So, you cannot really have a formula to allocate the functions. So, it actually depends on the creativity and the imagination of the designer, which is very crucial in allocating the functions to machines. And allocation can be systematized, combining imagination and systematization yields superior results. So, the second one says it can be systematized. So, we can have a systematic way of doing it, basically looking at the requirements, looking at the functional capabilities of the machine and looking at the risks involved in different tasks, we can do a systematic allotment. But if you combine the systematic allotment with the creativity or imagination, you can actually get superior results in allocation of functions. Another way of doing it is make use of analogous technologies building upon allocation decisions and their results. So, analogous technologies are the technologies existing in different other places or different other systems. So, you look at those technologies or the system analogous to the present one and build upon that one for allocation of functions and look at the decisions and the results in those analogous technologies, use them for allocating the functions to machines. So, some of the thing already existing, there are some machines which actually do some kind of task and there are some kind of allocation of functions to machines existing in some other fields. Then you look at that one and then see what kind of decisions are made for the allocation and what are the outcomes and what are the problems faced by them, and based on that we can actually have a systematic way of allotting functions. So, this is basically looking at the existing analogous system and then allocating functions accordingly. And another point to be taken care of the future technologies. So, we need to make sure that whatever the allocation we do, it actually caters to the future technologies also. So, the allocation decision cannot be solely based on what exists now. So, we need to look at the future and what kind of technologies exist or what are the possibilities of changes in technology, and accordingly we need to allocate the functions and ensure that the future technologies can be easily adapted, or when the technology improves, some of the functions previously done by human or some other system can be moved to the machine. So, that is the future technologies. There are a lot of developments taking place in the technology sector. So, there is a possibility that the work being done by human today can be done by a machine tomorrow. So, we need to have the functional structure in such a way that this task can be or the functions can be easily mapped to the machine at a later stage. That is why we should look at the future technologies and allocate functions accordingly. And again do it in stages and iterate many times. So, I do not do it the complete allocation at one go, do it in stages, allocate some of the functions and then iterate it many times and then see what are the possibilities and then complete the structure. So, do not do it in a single go, do it in stages and iterate. That actually helps us to identify the possibilities of failures or possibilities of interchanging components or the functions. If we do it in stages, if you do it in a single go, then we may lose the focus and then probably we do not really get the alternative architectures what we need. And provide interaction between the three design decisions. So, this is very important. As you know, the physical resources, function allocation and detailed design are the three design decisions. So, when we make a decision or design, we need to look at the physical resources available, we need to look at the function allocation, what are the functions to be provided and the physical resources, and then a detailed design of components. So, once we have these components, we need to go for identify the components, we need to go for the detailed design of these components. So, we need to provide sufficient interaction between these three stages. So, whatever may be the allocation we are doing, we should look at the physical resources available and the detailed design strategies or design requirements, and we should provide sufficient interaction between all these three in order to make sure that we have a good system or we have a perfect system at the end of all these three design decisions. That is the providing interaction between the design stages. And finally, assure the interdisciplinary communication. Again in allocation there will be multiple disciplines, multiple domains involved in the system. So, the communication between these disciplines or the domains becomes very important. So, we need to make sure that the function allocation actually takes care of the interdisciplinary communication and ensure that there are ways to communicate between these domains, or there is a common vocabulary or a common strategy for communication between these domains. So, these are the different principles on which the allocation of functions between human and machines to be based upon. So, in the previous one we discussed about the allocation of functions between human and the computer, and that was mainly based on the autonomy requirements, and this one actually discussed about the principles how we actually allocate functions between human and the machines. So, the one important points to be noted here are futuristic outlook, that is whenever there is a technology improvement we should be able to get the technology properly, we should be able to adapt to this technology. The other one is the interaction between different stages of design, that is the different elements of design, that is physical elements available, functional architecture, the allocation of functions, and the component design, that is the detailed design of components. So, these three should be, there should be sufficient interaction between them, and there should be a proper communication architecture or communication interface between different domains in the system. So, whether it is a mechanical domain or an electronics domain or a communication domain elements, we should identify the interdisciplinary communication requirements and accordingly provide the system architecture. So, these are the points to be taken care of while allocating functions. Another method of allocation of function is known as design structure matrix for allocation. So, design structure matrix is basically it will not again allocate the functions directly to the components, but actually it helps us to identify the interaction between different components, and then to identify some clusters of components or clusters of functions which can actually be used at the future stage to optimize the design activities or improve the design activities. So, this design structure matrix is meant to capture interactions of all sorts between functions, so that intelligent combinations of functions into components can be derived. So, basically we are trying to have combinations of functions into components. So, we can identify the functions and components and then see what kind of interactions are needed when during the design of these components, and based on that we can form some clusters. And this is a bottom up approach, because we start with the components and then try to identify the clusters. That is why it is known as a bottom up approach to the allocation of problem. And information in the matrix provides a clue as to how to rearrange the items to form clusters. So, here actually it provides a clue to rearrange the items to form clusters. I will take a very simple example, not a complete one, but a partially completed matrix to tell you how to use this one for allocation of functions or identifying clusters. So, look at this DSM, that is the matrix. You can see that these are the different components identified based on the functions and functional requirements. These are the components identified for a engine, that is V8 engine. Okay, this can be this is from Eppinger 1997. If you want, you can actually refer to this and then get the complete matrix. You can see here these are the different components. So, I can touch the engine block, cylinder head, camshaft, piston, connecting rod. Of course, there are many, I just shown only few over here. So, how do we make the matrix is that we write down these components on the rows, and then we write down the same thing A, B, C, D, E, F, G. So, this is A, B, C, D, E, F, G in the columns also, and then the rows actually represent. So, which are the inputs actually required by this particular block. Suppose engine block designer, what are the inputs required by them from other sources? Those are actually marked here circles over here, dark circles with strong interaction. So, you need a lot of information from B, that is the cylinder head, you need a lot of information from C, camshaft, you need a lot of information from D, that the pistons, and this interaction is not so strong. So, that is why it is shown as a very small circle. So, connecting rods you do not need to have that much of information for the design of engine block. Then like this, so you can have G is the flywheel and lubrication. So, you can see that flywheel information is not so important for the engine block, but lubrication is important. So, a lot of interactions are taking place here. So, like this you can actually identify the information required or the input required by this design team for designing the engine block. And the vertical the columns actually represent what are the outputs going from A to other design teams. For example, if you take the engine block design team A, output from A will be going to the cylinder head, the camshaft and the pistons, a very strong interaction. That means a lot of output from A is needed for B, C, D and others. So, similarly you can see that here the design team, the C team, the output from C will be used by these blocks. So, these design teams, of course this is not complete, but just an indicative of the interactions, but the interactions are represented by circles. Strong interaction or strong requirement of data is represented by a dark circle, and the other one is represented by a small circle. Now, looking at these interactions, it will be possible for us to identify which are the blocks should come together, because they have a lot of interaction, lot of data exchange is taking place. They need to discuss a lot between themselves to get the design successful. So, we will try to cluster them together and make them as a larger group. So, that is the idea of using DSM. We look at these and then try to have a blocks along the diagonals. So, wherever the interactions are more, we will put them together and then make it as a block, and that is done in the next one. You can see here. So, you can see here this engine block, crankshaft, flywheel, piston, connecting rod and lubrication, they have a lot of interaction between them, and that is why this has been made as a single block. Similarly, you can be identifying other blocks also along these lines based on the other components and their interaction, and we will try to identify the clusters of a design team who needs lot of interaction. So, this also helps us to allocate the functions accordingly, because the interactions are more over here, and therefore, we can actually have them clustered together to get the design effort in a better way, or to focus design effort. So, this is the use of DSM in application, identifying the functions to be allocated, or it will helps us to allocate functions accordingly. Okay, so that was about the allocation of functions and the different methods for allocation of functions and the principles to be used for allocation of functions, and other things to be done in important things to be carried out, or important activities to be carried out in the allocation architecture is basically, one is the trace non-input output requirements. So, we have input output requirements which are basically traced using IDF0 diagram, but there are other things to be done, basically internal input output requirements, system wide requirements, trade off requirements and qualification requirements. So, these need to be traced into the system when we develop the allocated architecture, and we will discuss this about the tracing of these non input output requirements in the next class. So, till we meet the next time, thank you and goodbye to all of you.